Here's a problem that involves adding vectors. Lou Reed drives this car, see, at 64 miles per hour northeast. And I guess I should assume that these guys mean directly northeast or due northeast, whatever the heck that means. That means 45 degrees away from north and 45 degrees away from east, just splitting the difference. While the ground spun underneath him at 620 miles per hour east. Oh, I guess we're going to be considering the rotation of the Earth now. Super. Okay, so Lou Reed's driving this car, right? And he's going directly northeast. So here's how we'll add vectors. What I want to do here is show graphical vector addition. That's what we're going to do now, and adding. Yeah, let's just call it graphical vector adding. We need to establish a scale. Our scale in this case should be something that can fit on our piece of paper, or if I'm working on the blackboard, it'll fit on the blackboard. I need to look at these two numbers and find something that I could use as a scale that will fit on this paper comfortably. And I need to get 620 miles per hour to the east. So I'm thinking, well, could 100 miles per hour be 1 centimeter? Then that vector there, 620, would be this long. That vector would be very, very short. So maybe I could double that. Maybe I could go up to 12 or something. So here's what I'll say. I'll say that 100 miles per hour is represented by 2 centimeters. How about that? Then in that case, 620 miles per hour would be represented by how much? Let's see, not 12, a little bit more than 12, 12.4 centimeters. All right. And then this guy right here, so I'll write 12.4 centimeters to represent that. And this is our scale. We can come back to this guy in a little bit. 64 miles per hour, that's going to be represented by 1.28 centimeters. 1.28 centimeters. That's what it seems like to me right now. And we'll have to add these guys. So here's my plan. I'm going to, number 2, draw tip to tail. Now, I didn't tell you what the tip of a vector is, nor did I tell you what the tail of a vector is. But if we try to draw tip to tail, that'll be one plus the other. It sort of shows one and then the other. So I can choose to write them in either order, but I'll choose to write the 64 directly northeast first. So what I need to do next, I guess, is establish a coordinate system. And I suppose I can't draw them tip to tail until I've established a coordinate system. So let's switch the order of those. My coordinate system is going to show north and east and east. So here's my coordinate system. Let's get, ooh, this is new. It's a red or rojo or rouge. Wow, that is a nice bold color. Everyone, you should support Crayola because that's awesome. This is north. And that's east right there. And I'm trying to figure out, how do I draw northeast? Well, I need 45 degrees away. Oh, shoot. How am I going to get, am I just going to approximate it? Not in the graphical method. I need to get it as close as possible. This is a protractor, my dear friends. And a protractor can be used in the following way. Let's not do purple. We're overdone on purple. Let's say I start with east, and I draw a dotted line to the east. So I'm going to make a little dotted line here. I'm going to be east, and I'm just going to right. Now I need to get away from the east. So I put this right at there, and I put that over to there, and that lines up with that right there. And I go over here to a 45, and I put a little tick mark at 45 degrees. And my vector doesn't need to be that long, but at least it's going to be pointing that direction. How long did I say that it needed to be? I think it needs to be, this first vector, 1.28 centimeters. So I'll go this direction, put that right there, go right there. 1.28 is a little bit less than 1.3. Our vector needs to go to right there. This is vector A. That's the velocity of the car. I'll name that guy vector A. And this guy right here, we could call that vector B. My plan is now to draw vector B. And vector B, vector B is much longer, 12.4 centimeters directly to the east. So, I'm gonna switch colors. I'm gonna switch colors. Green. This is not regular green, it's electric lime. And I'm gonna go directly to the east. Best way to show that is like that. So I'll aim there. I can see that parallel to that sheet of paper. So I'm gonna go here, and I'm gonna go over here, and I'm gonna go, how long? 12.4 centimeters. So I just go and go and go and go and go and go, and I get to 12.4, and I stop. Try this at home. Draw these suckers out. This is the graphical method of vector addition, homies. Here's what we need to do. There's vector B, and we've got vector A, and the resultant. Now this is the best fun. The most absolute best fun part is drawing the resultant. A resultant is a fun word that means result when you're adding two vectors. It is what comes of doing A and then B. And we're supposed to draw, see, here's the confusion. You're supposed to draw your vectors that you're adding tip to tail, and a lot of times my students then don't want to draw the resultant right. But the key is we're not drawing the resultant in order to add the resultant to anything. The resultant is what we get. So I say this statement right here, A vector plus B vector equals the resultant vector. So the resultant then needs to start where A and B start, like A and then B start right here. And the resultant needs to go where A and then B end. So the resultant needs to get to here. The resultant then will start and end where A plus B start and end, because the resultant is the same thing as A plus B. This is my resultant right there. And I need to know everything about the resultant. You see, the resultant is a vector. So as such, the resultant has two things. It's a quantity that has both magnitude and direction because it is a vector. We're probably gonna have these stupid units of meters or miles per hour. Ugh. Great. So let's find out how many miles per hour it is. We'll fill in that blank right there. And then we'll have to tell them which way Lou Reed's car is actually going. So I'm going to say at so-and-so of an angle, and we're probably going to have either north of east or east of north. We'll have to figure that out, and we'll hash that out in just a second. My plan, though, is to figure out how long this is. And I was hoping it would be something I could use trigonometry with or Pythag or something, but no. We cannot do this easily at all. There are no right triangles here. We are supposed to actually measure it and establish it with our scale. So I'm going to measure this sucker right here, and I'm going to measure it to be 13.5. You see that? I went here to 13.5. And then I note that 2 centimeters is 100 miles per hour, so 13.5 centimeters, what, 675 miles per hour? Yeah, check me on that. I think that's 13.5. Then, we need to find out what angle that points. And we have to specify it carefully. I see a reference point. This dotted line right here represents exactly to the east. So I'm going to compare my vector aura, which is a little bit away from east, to the exact east that's drawn right there. So let's call out this angle right here. That's the angle we're trying to find. I need to find that angle, and I don't know how to use trigonometry here because I don't have any right triangles. What I can do instead is get the protractor back. I look here, and I line that up with the base, and I see that that is, wow, just about 5 degrees. How about that? We're not doing sig figs here. We're being kind of sloppy. If I were doing sig figs, I would have to change this to 680 miles per hour. And let's say that, wow, that's pretty darn exact there. That's at 5.0 degrees. It's very close to directly east. It's only 5 degrees away from east. See that right there? 5 degrees away from east. So I can say, what is it, north of east or south of east by 5 degrees? It's very close to east, right? Very close to east. So I'm gonna say that it's just 5 degrees north of east. It is only 5 degrees north of east because it's just barely up from the east direction. Anyway, that's how you add vectors graphically. It is a terribly, terribly error-prone method because if I didn't draw that angle or that length exactly right, and if I didn't start at exactly the right place right there, and if I didn't draw that angle exactly right and that length exactly right, and if I didn't measure it all right, you see, so many things can go wrong. That really bothers me because I like to be precise. We're trying to do science here. This process here, this feels like I'm drawing pictures. I'm not very good at drawing pictures, and I hate. What I do is I sit, and I hate, and I loathe, and I want to destroy when I think about the graphical method of vector addition. So I'm going to stop this because this is getting a little bit out of hand. You should know the graphical method of vector addition, but probably not ever use the graphical method of vector addition. I'm leaving. Here's a problem that involves adding vectors. Lou Reed drives this car, see, at 64 miles per hour northeast. And I guess I should assume that these guys mean directly northeast or due northeast, whatever the heck that means. That means 45 degrees away from north. And what I want to do here is show graphical vector addition. That's what we're going to do now, and, adding. Yeah, let's just call it that, graphical vector adding. We need to establish a scale. 45 degrees away from east, just splitting the difference. While the ground spun underneath him at 620 miles per hour east. Oh, I guess we're going to be considering the rotation of the Earth now. Super. Okay, so Lou Reed's driving this car, right? And he's going directly northeast. So here's how we'll add vectors. East. So I'm thinking, well, could 100 miles per hour be 1 centimeter? Then that vector there, 620, would be this long. That vector would be very, very short. So maybe I could double that. Maybe I could go up to 12 or something. So here's our scale. In this case should be something that can fit on our piece of paper, or if I'm working on the blackboard, it'll fit on the blackboard. I need to look at these two numbers and find something that I could use as a scale that will fit on this paper comfortably. And I need to get 620 miles per hour to the